So what we've tried to emphasize so far in talking about our angular quantities is that these ideas, these concepts, and the problems that we're working with these concepts are very much analogous to what we did with our linear quantities. And that's also true when we're talking about angular momentum. So the conservation of angular momentum is very similar in terms of both the idea behind it and then the way that we're going to work problems as the conservation of linear momentum. So to set up the conservation of angular momentum, let's actually start by remembering what we set up when we were talking about the conservation of linear momentum. So one way to set that up is to say, well, let's start with the translational version of Newton's second law, which tells us that the net force acting on our object, or on our system, is equal to the time rate of change of the linear momentum of our system. So all we're going to do is we're going to take this equation and basically just rewrite it. So solve for our dp term. So when I do that, I get that this infinitesimal little change in the linear momentum of my system is equal to the net force times dt. And all I want to do is recognize that I can break up the net force into two types of forces. Internal forces, forces that are caused by parts of my system acting on other parts of my system. And then external forces, forces that are felt by pieces of my system but are caused by things that aren't in the system. And what Newton's third law tells me is that when I add up all these internal forces, they're all going to cancel out because for every single internal force, it's got a Newton's third law pair that has an equal magnitude and opposite direction. And so when I add them together, they always add up to be zero. So this tells me that this infinitesimal change in the linear momentum of my system is equal to the net external force acting on my system times dt. And so what this really means is that how the net external force acts on my system over some tiny little chunk of time dt, that's going to cause infinitesimal changes to the linear momentum. So again, this is highlighting that having an external force, a net external force acting on your system is precisely what's going to cause the linear momentum of your system to change. So what we can do then is we can integrate this equation. And so in doing that, I'm going to integrate the left-hand side from some initial to some final momentum. I'm going to integrate the right-hand side from some initial to some final time. And this is what I get. I get that the change in the linear momentum of my system is equal to this integral from initial to final time of the net external force acting on my system times dt. So what this equation is telling me is, again, that the change in the linear momentum of my system is due to the fact that the external forces act on your system over time. That's what causes that change. I can take this equation and rewrite it, so basically break apart the change in linear momentum term into final minus initial, put the final on one side, put the initial on the other, and so I'm left with this equation. And we said the nice thing about this equation is it's basically set up to help me keep track of the linear momentum of my system. It says that what you start with, right, the total initial linear momentum of your system, plus this integral that allows you to change the linear momentum of my system, is going to tell you what the linear momentum of your system is at the end. And again, in class, we called this the linear momentum equation. So some important details that this equation was trying to convey. Well, the first was, again, it explicitly tells us what causes the linear momentum of each system to change. It's this integral term. And this integral term, basically, we gave it a name. We said this is equal to what we're going to call the impulse. So this was J. And again, this is really the net external impulse, or the impulse due to the net external force acting on your system. Well, what about when J was 0? So, of course, if the impulse on our system was 0, what that means is that the linear momentum of our system has to be conserved. So if this term that can change the linear momentum of your equation, if that's equal to 0, then that tells you that your initial and final have to be the same thing. And the easiest way to make the impulse be 0 is to say that the net external force acting on your system is 0. So when the net external force acting on the system was 0, that meant that the linear momentum of our system was conserved. The other detail that we had to remember, of course, is that this is a vector equation. So again, there's a, in the way that we tend to, in introductory level physics, work in 2 dimensions, we're going to break this up into 2 equations. So here's our x equation telling us about the x component of the initial momentum of our system plus the x component of the impulse. That's got to equal the x component of the final momentum of the system. Same thing's true in y. So we have a y component equation with the y component of the initial linear momentum of our system plus the y component of the impulse. That's got to be equal to the y component of the final momentum of the system. And again, we can have a situation where the x component of the impulse is 0. And if that's true, then that tells me that the x component of my linear momentum is conserved. If, on the other hand, the y component of the impulse is 0, then that means that the y component of my linear momentum is also conserved. So whenever my impulse has a component that is equal to 0, that means that that component of the linear momentum will be conserved. So as a simple example, again, we can talk about, say, totally inelastic collisions between 2 particles. So here's mass 1, and let's say we're looking from above, so let's let mass 1 be moving north, we'll let mass 2 be moving east. These 2 particles are going to collide with each other, so here's our initial picture. Because it's a totally inelastic collision, they're going to stick together, and the 2 of them will move off with some final velocity that points up in some direction like this. And so again, when we think about what's going on within this collision, the first thing that we recognize is that the net external force acting here is going to be equal to 0. Mass 1 is going to exert a force on mass 2. Mass 2 is going to exert a force on mass 1, but those forces are internal to my system. And everything else, all the other forces, cancel out. So the net external force is 0, which means that the impulse is 0. The impulse being 0 tells me that the linear momentum of my system will be conserved. And so I can break this up into, I can pick x and y coordinates, an x and y coordinate system for this problem, then break my conservation of linear momentum equation up into x and y components. And so for my x component, I recognize that mass 1 does not have an x component initially. Mass 2 is entirely in the positive x direction. So I've got 2 pieces initially. They stick together to give me a single piece at the end, so I can treat this as just a simple total mass, and then the x component of that final velocity. Setting up my y equation, I see the same thing, right? All of mass 1's initial momentum is in positive y. Mass 2, its y component for the initial momentum is 0. So my 2 pieces initially give me a y component that looks like this. Again, they stick together, so I can basically treat them as a single object at the end with a total mass of m1 plus m2, and again, they're going to have some y component of the final velocity vector. So this was how we worked conservation of linear momentum. Conservation of angular momentum is very simple. So the only real difference is we're just going to start with the rotational version of Newton's second law rather than the translational version. So this equation, the rotational version of Newton's second law, tells me that the net torque acting on my system is equal to the time rate of change of the angular momentum of my system. So we're going to do the same thing. We're going to solve this equation for dl. So for the infinitesimal change in the angular momentum of my system, and again I see that that's got to be equal to the net torque times dt. And I can break up the net torque into think about internal torques, right? So torques that pieces within my system exert on each other, and external torques, torques that pieces in my system feel that are caused by things outside my system. And again, because of the way these forces are acting, these internal torques are all going to cancel out. So I'm left with an infinitesimal change in the angular momentum of my system is equal to the net external torque acting on my system times dt. And again, this tells me that how the net external torque acts on my system over some infinitesimal amount of time dt, that's going to cause infinitesimal changes to the angular momentum of my system. So again, it's highlighting that the net external torque acting on your system over time is what changes the linear momentum, or the angular momentum of your system. So we can go ahead and integrate this equation. I can integrate the left-hand side from some initial to some final angular momentum. I can integrate the right-hand side from some initial to some final time. And again, I get that the change in the angular momentum of my system is equal to this integral from some initial time to some final time of the net external force acting on my system being integrated over time. So this integral that depends on the net external torque and how it acts on my system over time, that's what's going to change the angular momentum of my system. If I break up this change in the angular momentum, final minus initial, and again sort of take one of those, take the initial term over to the other side of the equation, then this equation again is set up to help me keep track of the angular momentum of my system. It says that how much I start with, the initial angular momentum of my system, plus this integral that can change the angular momentum of my system, that's going to give me the final angular momentum of my system. And so unsurprisingly, we will refer to this as our angular momentum equation. Now again, the angular momentum equation, there's some important details that I need to remember when I'm working with this equation. So the first one, very similarly, is it tells me what causes the angular momentum of a system to change. It's this integral, and again, we're going to give this integral a name. We're going to call it the angular impulse. So this is the angular impulse exerted or caused by the net external torque acting on our system over some time. Well, when the angular impulse is 0, so if this integral, when I add it up, it's equal to 0, that tells me that the angular momentum of my system is going to be conserved. So if this term that can change the angular momentum of my system is 0, that means that my angular momentum isn't going to change, which is another way of saying it's conserved. Again, the easiest way for the angular impulse to be 0 is for the net external torque acting on the system to be 0. So when the net external torque acting on the system is 0, that's when we're going to have conservation of angular momentum. Well, this is also a vector equation. And for our class, where we're going to tend to deal with forces that act within the plane, so that then we can think about how that's causing our system to rotate about an axis going into and out of that plane, we have a single equation. Right? So we're going to tend to deal with problems where we're just going to worry about the angular momentum in z. And if the z component of the angular impulse is 0, that means that the z component of the angular momentum is conserved. Now, you may in further classes deal with situations where you have angular momentum conservation in one component, but not in others. And so again, this is just, it's entirely a function of how many components of your angular impulse are equal to 0. So whenever the component of your angular impulse is equal to 0, that's when you're going to have conservation of angular momentum for that component. Now the other detail that we have to deal with for conservation of angular momentum that we didn't have to deal with linear momentum is the idea that angular momentum and angular impulse care about your choice of pivot. So if we really wanted to write out this equation, there's really sort of an additional subscript we could add that says, we're basically going to read this backward, right? The initial angular momentum of the system about point O. That's what I start with, because it cares, my angular momentum cares about my choice of pivot point. Plus the external angular impulse exerted on my system about point O. So again, I've got to calculate the angular impulse about the same pivot as I'm calculating the angular momentum. But if I do that correctly, add those two things up, it's going to tell me what the final angular momentum of my system is about point O. So we often don't write this subscript. We very rarely say it, but it's critically important that we remember that all these things, all these angular quantities, depend on your choice of pivot. So in terms of an example, let's look at a totally inelastic collision between a particle and a rod of length L that can pivot around one end. So here's a situation where clearly this is the pivot that we're interested in. Initially, let's say my mass happens to be moving so that it's going to hit this rod perpendicular to the rod, and mass 1's moving with some initial velocity. The rod's just sitting there, it's not rotating at all. Well, since it's a totally inelastic collision, the mass is going to stick to the rod, and then this whole thing is going to start swinging up as it begins to rotate about the pivot point. So I have no angular momentum for the rod initially. I do have an angular momentum for mass 1 that I can calculate, and I'm going to have an angular velocity for my rod at the end that I'm going to be able to relate to the angular momentum. So because in this case, again, the net external torque acting on my system is 0, which means that the external the angular impulse on my system is 0. So the particle is going to exert a torque on the rod. The rod is going to exert a torque on the particle. But those are internal. I don't have any other forces that are acting on this system during the collision to try and change the linear momentum. So the angular impulse is 0, which means that the linear momentum of my system is conserved. And again, really, it's conserved. What we mean is the angular momentum of this system is conserved about this pivot point in the z direction, because really this is a one-dimensional problem. So I'm going to pick positive z to be in the direction that the initial angular momentum of my system is. It's going to be also the direction of the final angular momentum of my system. And so now that I've picked that to be the positive z direction, I can set up my equation. Again, I just have a one-dimensional equation. Signs matter. My particle has an angular momentum in the positive z direction initially. The rod doesn't because it's not initially rotating. At the end, once they've stuck together, I basically have a single particle, or a single entity, a single object that can rotate around this point. That I can use the parallel axis theorem to figure out what the moment of inertia is for the rod here. I can use my calculating the moment of inertia for a particle to figure out what the moment of inertia for mass 1 is. Add those two things up, that's going to give me the moment of inertia of this system after they've stuck together, and then this whole thing is rotating with some final angular speed that happens to also be in the positive z direction. So here's my equation that I'm setting up due to conservation of angular momentum. It again looks very much like a one-dimensional, totally inelastic collision. It's just in this case, my one-dimensional, totally inelastic collision is an angular, is for the angular momentum coming out of the page. And so this is the way that we're going to work conservation of angular momentum problems in class. We're going to pay attention to initial, final. We're going to think about the pieces we have in our system initially, the pieces we have in our system at the end. We're going to think about direction, because again, this is a vector problem, so we need to pick a positive and negative direction for our coordinate system to make sure that we keep our signs straight. And then we'll deal with situations where the angular impulse is 0, so that we have conservation of angular